This lecture is going to be about the difference between temperature, internal or thermal energy, and heat. These are words that all seem very similar to each other, but all have very different, very specific definitions. Before we talk about these three ideas, I need to talk about the kinetic theory of matter, because this is a concept that's going to be guiding our entire understanding of basically this entire unit of material. Everything that we talk about will tie back to this central concept. All matter is made up of a large number of tiny particles, and the microscopic or small behavior of the particles determines the macroscopic or large behavior of the material. As an example of what I mean by the kinetic theory of matter, we can compare ice and water with each other, and I know that ice and water are the same fundamental thing. They're both made of H2O, but ice and water have different temperatures and different properties. Ice feels very cold, it's a solid, and water feels probably warmer and it's a liquid. Now I know that these two things are fundamentally the same as each other. They're both made of H2O. So I want to know where the difference comes from. Why is it that ice is a solid and feels cold and water is a liquid and feels warm? And the only difference, the only physical difference that's causing these two things made of the same material to behave differently is the behavior of the very, very tiny particles like the molecules that make these objects up. If we were to zoom in, like I'm showing in the black boxes, and observe what the particles in each material are doing, we'd see something like this. In the ice, the particles that make it up are all kind of stuck together and shaking, but just a tiny little bit. They have just a little bit of motion as they move back and forth around each other. The overall structure doesn't really change its shape. And in the water, I can see that the particles are much more free to move around in random directions, but still stay kind of close together, but they're moving a lot more as well. So when we experience temperature, when we experience something as being hot or cold, that's actually just our brain signal telling us how much these particles are moving. And when we experience something as being a solid or a liquid, all that really is how much the particles are able to hold each other together. If they're able to hold each other together very strongly, you can see they behave as a solid, and if they can't really hold each other together, they behave as something like a liquid. So this big idea is going to be guiding the entire unit. The macroscopic or large behavior of objects in terms of temperature and heat really depends on the small movements of the small particles that make these objects up. There are three words in the subject that appear to be very similar, but all have different meanings. Temperature, and then either internal energy or thermal energy, whatever you want to call it, and heat. Temperature is a measurement of the average kinetic energy per particle in a material. Its variable is capital T, and we measure it in degrees Celsius or Kelvin. Internal energy or thermal energy is a measurement of the total kinetic energy of particles in a substance plus the total potential energy of the bonds between the particles. Its variable is E int, and the unit is J, or the joule, because it's a form of energy. Heat is the total change in thermal energy, or the final thermal energy minus the beginning thermal energy. So heat is a change in energy, and we use the variable capital Q to symbolize heat. And because it's a change in energy, it's also measured in units of joules. So what's the difference between temperature and internal energy? They seem very similar to each other. Temperature is the average kinetic energy per particle, and internal energy is the total internal energy of all the particles in the material. Intuitively, those two things don't sound too different from each other, so I'm going to give you a few intuitions about the exact definition of temperature and internal energy and how they're different from each other. I'm going to imagine that we have two materials, one on the left and one on the right, and I can see the particles in the material. And I can also see how much kinetic energy each particle contains. So I've written that in the center of each particle. The temperature is the average kinetic energy per particle, so to find that average for the material on the left, I can just add the total kinetic energy and divide it by the number of particles. So I can see that this material has an average kinetic energy of 3 joules per particle. On average, of the two particles, each one has an average of 3 joules. So that would be a way of recording the temperature. The internal energy is the total energy that exists in the material. So the total energy here would just be 6 joules. So that's a way of understanding the difference between temperature and internal energy. Temperature is an average energy per particle, and internal energy is just the total sum of the energy that you have in a material. If we look at the material on the right, and we find its average kinetic energy per particle, I find that that's actually also 3 joules per particle. So these two materials actually have the same temperature as each other because they have the same average kinetic energy as each other. But their internal energy is very different. I can see that the internal energy of the material on the right is much greater than the internal energy of the material on the left. So these two sets of particles have the same temperature, but different internal energy. So this is one way of showing the difference between what we mean by temperature and what we mean by internal or thermal energy. Another example could be a heated pool where we have a lot of hot water inside. We take a bucket and take just a little bit of hot water out of the heated pool. Because the particles in the bucket are on average moving in the same way as the particles in the pool, I would assume that the temperature of the pool is the same as the temperature of the water in the bucket. But because there are so many more particles in the pool than in the bucket, those particles must in total have more energy than what's contained in the bucket. There's more total thermal energy in the pool than there is in just the little bucket, and so we would say that the energy in the pool is greater than the energy in the bucket. So that's another way of understanding the difference between temperature and internal energy. This last note that I'm going to make is a little complicated. We're going to talk about it a lot more in future videos. Temperature is only affected by the kinetic energy in particles, but internal energy is a measurement of both the kinetic and potential energy of particles. Potential energy exists in the bonds between the particles holding them together. We'll focus on this more in the phase change and temperature versus heat graphs lectures later in this series. So just as an example, we can make a graph of the kinetic and potential energy of a material. It looks a little weird. It looks like this. I'll explain why that is in a future video. But if I begin to change the kinetic and potential energy, you'll notice that the temperature is only affected by the kinetic energy, and when I change the potential energy, that changes the bonds between the particles, but it doesn't change the temperature. So temperature is only a measurement of the kinetic energy in a material, whereas the internal energy is a measurement of the total amount of potential and kinetic energy together. So again, that's a little complicated. You just have to remember that that difference exists, and I'll go into that in more detail in future lectures. There are three common units for temperature, and we only use two of them in science: Fahrenheit, Celsius, and Kelvin, and we only use Celsius and Kelvin when we're working in science. These have just been adjusted to make more sense scientifically. The table on the left shows some important temperatures on each scale. You can see that we have the lowest possible temperature that can be reached on each scale, the temperature at which water freezes, and the temperature at which water boils. On the right, I have a table showing ways of converting from each unit of temperature to each other unit of temperature. Notice on the chart that a change in 1 degree Celsius is equal to a change of 1 degree Kelvin. When you go up 100 degrees Celsius on the left, you also go up 100 degrees Kelvin on the right. This will matter when we're doing math with temperature. A change in temperature in terms of Celsius is always equal to a change in temperature in terms of Kelvin. They're always the same number. The kinetic theory of matter says that what we experience as temperature is actually just the average kinetic energy of particles. This means that there's a lowest possible temperature an object can have, a point where all the particles inside it have no kinetic energy at all and are not moving. We call this temperature absolute zero. But it's physically impossible to actually get to absolute zero just because of some other laws of the universe. But if we could get to absolute zero, the picture on the bottom right is what it would look like. All the particles just completely frozen in place. Because it's not possible to have less motion than no motion, it's not possible to have less temperature than the absolute 0 point of temperature. So you can see that that's 0 degrees on the Kelvin scale. That's actually how the Kelvin scale was developed. It started from a point of absolute 0. It's negative 273 on the Celsius scale and negative 459 on the Fahrenheit scale. So there is a lowest possible temperature that you can reach. Absolute zero temperature does not occur anywhere on Earth or actually anywhere in the universe, and this means that even very cold material still has some internal energy. This can be a little confusing for students because they don't normally think of cold things like snow as having thermal energy. They usually only think of hotter things like burning wood or lava or something like that as having thermal energy. But actually, as long as a material is not at absolute zero, that means that its particles are moving a little bit, which means that there's still some internal thermal energy. So even very cold material like snow has that internal energy. And it's actually possible for a lot of cold material to have more total internal energy than a little hot material. If we were to compare the total internal energy in all the snow on Mount Everest, as an example, and compared that to the internal energy of wood in a fire, we would actually find that the snow had more internal energy in total, because if we were to add up all the small amounts of kinetic energy in all the little bits of snow in the mountain, that very large amount of very small quantities would actually add together to be more than the small amount of large quantities of kinetic energy in the wood. So even though the particles in the wood are moving much faster than in the snow, there are so many more particles of snow that the total internal energy is greater in the snow than in the fire. Now that we've addressed temperature and internal energy, the last subject to talk about is heat. Heat is the change in thermal energy, and because work is another name for the change in energy, heat can also be described as the thermal work done by or on a system. This has its own name and symbol because thermal energy often changes and moves from one object to another, so we need a specific mathematical symbol for that because that's going to come up a lot in very specific equations. As an example, if the blue object had 100 joules of internal energy and the green object had 40 joules of internal energy, and we imagine that we transferred 20 joules of energy from the blue object to the green object, the heat emitted by the blue object and gained by the green object would be 20 joules. And so the blue object would be reduced by 20 and the green would be increased by 20. Because energy is conserved, which means it cannot be created or destroyed, the heat emitted by one object must be the same as the heat gained by the object receiving it. So if we imagine that we're giving heat from object 1 to object 2, I know that the heat lost from object 1 will be equal to the heat gained by object 2. Just going back to our other example, in this example 20 joules were lost from the blue object and gained by the green object, and I can see that that makes the equation on the bottom work. So that's everything that you need to know about the difference between temperature, internal energy, and heat. These are the definitions, variables, and units again. And just remember that all our understanding of this material comes from the central idea of the kinetic theory of matter, which says that, again, matter is made up of a large number of tiny particles, and the microscopic behavior of the particles determines the macroscopic behavior of the material. This will come up a lot as we begin to explore this topic more in the next few videos.